Hello students, today we have fifth assignment of chapter 10 wave optics. In this assignment we'll introduce ourselves to a new phenomenon diffraction. So in first question we'll see two definitions of diffraction. In next part we'll understand why we can listen to a person on the other side of an open door who is standing behind wall, but we cannot see that person. Why does that happen? And lastly, in this video, we'll see that central maximum of diffraction pattern due to single slit is always bright. The next two questions we will address in next video. So let us start with understanding of what is diffraction. We know that, suppose if we take a torch and light is coming out of the torch and there is a wall, so we know that the light follows this path and this is how we get light from the torch, isn't it? So uh, large portion of the wall gets illuminated because of this. Now consider another situation where we have the same torch, but now the torch is placed in such a way that there is a wall. Between the bigger wall, there is a curtain, let it be curtain or window. And now when the torch is switched on, the light is obviously falling on this lower part of the wall. But what about this part of the wall? Will it get any light? So we know that practically we expect that as light travels on straight path, it should be restricted to this region. Light should be restricted to this region of wall. But in a real-time situation, if you observe, you will see that some light is going here also. And even in this part, we get some intensity, maybe less, but there is some intensity. It means that the incident light has bent and reached up to this region. So this shows that whenever light is obstructed, it changes its path, it bends. Now, the interesting part here is the refractive index here is same. So it's not refraction. It's the change in direction is not because of change in medium. It is because of some presence of some obstruction. Okay, and this phenomena is called diffraction. So what is diffraction? Diffraction is one definition of diffraction says that whenever light is obstructed, it changes its path, it bends. This is diffraction. Second way of explaining it is that if you take a door, means slit, you see that light is producing some effect pattern here, and this is because limited part of wavefront is allowed to pass through this window or slit. So effect produced because of limited part of wavefront is diffraction. That is second definition of diffraction. And we all have experienced this situation. Suppose you are in a room and say you are here and there is some person here, let us say A and B. Now this is door, so B cannot see A. But suppose if A speaks something, then definitely the sound of A reaches B. Now, why does that happen? Light is also wave, sound is also wave. So, why sound waves can reach B but not light waves? The reason is this bending of this wave theta is directly proportional to lambda and inversely proportional to width of this slit. This is width d. Okay, so if you compare lambda of sound, now here d is constant for light wave and sound wave, door is same, so d is constant. So I can say that bending or diffraction is proportional to lambda. Now lambda of sound which is in terms of meter, is very greater than lambda of light, which is in terms of angstrom, 10 raised to minus 10 meter. Okay, this is 10 raised to 0 meter, few meters. So there is vast difference between the two lambda, and hence the bending of audio wave, sound wave is much higher than bending of light waves. And because of that, B can listen to A, but B cannot see A. Okay. Now let us move to next part, third question of this assignment. Just like interference, in diffraction also we get regions of higher and lower intensity. So consider a slit, and let this be the center of the screen, which is exactly in front of the slit. Let the width of the slit be D. Okay, and so to focus all the waves which are bent towards A, we consider a lens we placed here, and now there is a wavefront approaching, and in this wavefront we consider A, B, and C, three waves we consider. So as the waves pass through this lens, they will reach O point. Let these points be A prime, B prime, and C prime. So now we know that up to this point there is no path difference. Okay, so if there is path difference, which apparently is there, look at A prime O and B prime O. Definitely these two are not having same length. Though C prime and O appears to be equal to A prime O. So what should be the situation of O? Should it be bright or dark? We know that condition for bright fringe to take place is path difference should be n lambda. Okay. Now here there is path difference, but how do we know it is n lambda or not? Now first line itself is wrong. There is no path difference. Why there is no path difference? Look at the situation once again. These waves are traveling different distance in lengths. So this wave is traveling less distance as compared to middle one, as compared to middle one is traveling more distance as compared to upper one. So though this one is traveling more distance in air, the time for A prime wave to reach O and time for B prime wave to reach O will remain same. We feel that A prime O is longer path compared to B prime O, and hence this wave will reach first, but it is not so. Why? This distance is more. Okay, so you may say that optical distance traveled is same for all the three waves. One is traveling more distance in air, other is traveling less distance. This is traveling less distance in air, but more distance in glass. And hence, ultimately they reach at same time uh, at point O, and hence there is no path difference. So what happens to the central point in the diffraction pattern of single slit? Answer: the central point is always bright because there is no optical path difference between the waves reaching the center. Okay, so that was the topic. Thank you.